Okay. So this problem that we just did, all of the math would have been a bit simpler if we would have been in a rotated coordinate system. And in Physics 1, you remember doing it all in a rotating coordinate system. I want to just mention for the first time, this is going to come up again, but a really easy way to go between coordinate systems. So this is a way to re-express vectors in rotated coordinate systems.
Can I make a request?
Yes.
15 minutes before the end of the class, can you kind of go over what we kind of have to go over?
Oh, for the test. Yeah, that's a good idea. So re-express vectors in a rotated coordinate system, and the way we're going to do it is most likely not the way that you did it before, but it's a really nice, quick, efficient way, and it's an important thing to understand as you go on in your later classes. So we're going to use rotation matrices. So we're going to do it in 2D, and this generalizes to 3D, but in this class, this is all we're going to need. So if you want to okay, forget that. If you have a vector expressed in coordinate system A, let's say that, so this is how you have the vector expressed. And you want to re-express that vector in coordinate system B, and let's say that this is our coordinate system B. You want to find the angle theta and this has the usual sign convention of positive being counterclockwise to get from A to B. Okay, so if we started here, and we want to express it here, and let's say that that angle there is theta. Is this a clockwise or a counterclockwise rotation? Counter, so theta is positive, right? Then your rotation matrix, we'll call it Q, under squiggle means matrix. The matrix is always of the form cosine theta, sine theta, negative sine theta, cosine theta. And then your vector expressed in the B coordinate system is equal to the matrix Q times the vector that you started with expressed in the A coordinate system. It looks like a pain when you're not used to matrix calculations, or if you have to do these calculations by hand, but all of your calculators do them for you. And so when you get used to this, this is a really nice, quick way to do it. So I want to just show one of these vectors, how this rotation would work. Has everyone, or who has seen matrix multiplication before? Okay, almost everybody. So I'll just quickly write down how it works for a 2x2 matrix. So if we have a matrix A, B, C, D, and we're multiplying it times a vector E, F, we get A, E plus B, F. And you can think of that as like a dot product between this and this. And then for the second one, we have CE plus DF. So that's all we're doing. And you don't even have to remember how to do that. You just have to know how to do it on your calculator. So from the previous example, let's find one of these vectors. Okay, so let's go back to one of these free body diagrams. So free body diagram 1. T1, T2, N1, and then the weight. And all of these are easy to do in a coordinate system like this, right? Well, the weight is the only one that's easier in the standard coordinate system. So let's express T1, T2, and N1 in this coordinate system, and then we'll use the rotation matrix to put it in the new coordinate system, and it better match up with what we did. Okay? I mean, it's really not that urgent, but I hope it does. So our coordinate system B is this. Okay, so what angle? So remember, this angle's 30 degrees. What's the angle theta that we need to go from coordinate system A to coordinate system B? Positive 30, yep. So theta is equal to positive 30 degrees, which means that our rotation matrix is cosine 30, sine 30, negative sine 30, cosine 30. And in decimals, that's 0.866, 0.5, negative 0.5, positive 0.866. All right, so let's first do T1. The force vector in the new coordinate system is equal to 0.866, 0.5, negative 0.5, positive 0.866 times, what would this vector T1 be in coordinate system A? Negative T1, 0. It's in the negative x direction. And you do that multiplication, and you get negative 0.866 T1, positive 0.5 T1. Is that what we got before? I'm afraid to look. Matches. Yay. Okay, so T2, now I'm feeling more confident. So the force 2 in coordinate system B is going to be equal to the same matrix in coordinate system A. What would this force be? It's in the positive x direction. So T2, 0. So you get positive 0.866 T2, negative 0.5 T2, and that matches. And then the last one is the N1. So like the normal force expressed in the B coordinate system, rotation matrix, and in coordinate system A, what would this normal force be? What would the components be? 0 and 1, yep. So you get 0.5 N1, 0.866 N1. It's pretty quick with a TI calculator because it does those matrix calculations really easily. I think in a lot of textbooks and stuff, matrix calculations are kind of de-emphasized because it's a nuisance to do by hand. When these books were developed, it wasn't easy to use matrix approaches, but now it's super easy. You can do it. You can do it in Excel. You can do it on your calculator. You can do it in MATLAB. You can find matrix calculators online and do it that way. But it's even easier if you enter in programs in your calculator that simplify some of these functions. And I'm pretty sure that in the materials section on D2L, there's a list of TI programs that you can enter into your calculator. And one of them is entering in a thing for rotation matrices where you just enter in theta and it spits out the matrix for you. And so it's way, way faster than drawing out the right triangles and figure out the components or however otherwise you would do those rotations. And then try doing it in 3D. It's impossible to do it you can't do it by drawing out right triangles and stuff, but this is the exact way that you do it in 3 dimensions. You just have a 3 by 3 matrix instead of 2 by 2. Okay, we'll come back to that. Anybody have any questions about, so that's the end of what I want to say about particle statics. Anyone have any questions about that or the rotation matrices or anything right now? Yep.
So if you're rotating, depending on whether you're rotating clockwise or counterclockwise,
Yes.
does the equation change?
Yeah, the format that matrix stays the same. All that changes is the sign of theta. So if you had if you had your value, where is that? So if this was your coordinate system A and you wanted to re-express it in this one, you would just enter in a theta of negative 30 degrees or whatever. You know what I mean? But it still would be cosine sine, negative sine cosine.
Can you scroll up, please?
Any other questions? All right. So now we're going to go on to rigid bodies. And the change when you go from particles to rigid bodies is now we're dealing with objects that do have length dimensions, and therefore different parts, we make distinctions between different parts of the body, and therefore orientation matters. So we're going to have to deal with the rotations of bodies, which we haven't had to before. So objects have length dimensions, and therefore orientation matters. For example, the kind of thing that we'll be considering. So this is supposed to be like a top view of a car. That looks terrible. No. Okay, so consider two cases. Same car. Don't patronize me.
Is it like a tri-wheel car over there on the left?
Yeah, that's a good. Thank you. What?
Oh, is it turning?
Oh, yeah. It's on ice. So it's not gonna matter the direction of the wheels. Okay, I didn't tell you that yet, but yes, it's on ice. And think about these two cases. So first, you apply a 50,000 Newton force there, and second, you apply a 50,000 Newton force there. With particle analysis, you can calculate the acceleration of the center of mass of the cars in both of these two cases, and it's going to be identical. The acceleration of the center of mass in this case is going to be the same as this one. But in this case, where this force isn't applied through the center of mass, you can imagine this is going to have a lot of, spinning angular acceleration in addition to the translational acceleration of the center of mass. And so now we want to deal with cases where we consider the distinctions between these two cases. We're not assuming that everything happens at a single point at the center of mass anymore. And a key concept for this new consideration of an object's orientation is the moment of a force about a point. People usually call it moment, or in physics, they're more likely to call it interchangeable, say that's the same thing as torque. In engineering, you tend to think of a torque as specifically a twisting, equal and opposite twisting on the ends of some kind of, long shaft or bar. But either way, people usually leave off this part, and it's an important part of the definition of what we're talking about. So even though we're going to call it a moment often, be sure you remember that we're talking about the moment of a force about a point. And the definition of a moment of a force about a point is that the moment about A is equal to a row vector crossed with a force vector. So that's the definition, and I'll tell you what these things are. Where rho is the vector going from the about point A, you know, the point that you're calculating the moment about, to the point where the force is applied. And F is the force vector. Okay, so here's a diagram. So here's just some, random rigid body. And we want to calculate the moment applied by this force F around this point of rotation. So the row vector then goes from, if you think of, let's call this point where the force is applied, the point P, okay? Then the row vector goes from A to P. Nope. Like that. And then you take the cross product rho with F, and that gives you the moment. So the moment produced by this force depends on the force, and it also depends on the location of the force and the location of the about point. Is that the same thing as F cross rho? No, with cross product the order matters. So if you do F cross rho, you'll get the opposite, the signs will all be switched from the right answer. The best way, I think the easiest intuitive picture, I knew I missed some stuff. Intuitively, think of a moment in terms of a wrench turning a bolt. So if this is the bolt, and you're trying to make it turn around its center, so that's the about point there, right at the middle. And this is the wrench. Say there are two places where you can apply this force F to make that, this bolt's stuck. You're trying to generate a big torque to make it turn. Which one of these is going to be more effective in making it turn? Yeah, you want to, you know from using wrenches before that you want to apply the force as far from the axis as possible, and that's because this is the row vector. And in this case, the row vector is perpendicular to F, so you just have the magnitude of that row vector, just the length of row times the magnitude of F, and that gives you your moment. So the smaller this is, the smaller the moment. The bigger it is, the bigger the moment. If you took this force, or 1,000 times this force or whatever, and applied it so that the line of action of the force acted right through the axis of the bolt, it would never turn. It would just eventually rip the bolt in half, which is very frustrating. So don't do that. And this is the last thing I want to say today. I want to introduce this. You can take it or leave it, but people seem to find this use. Oh, no, before I do that. One thing to notice here. And this is a property of the cross product, and it's something that we're always going to see. The moment is always a vector. That's a property of cross product. The inputs are two vectors, and the output is a vector. If all of your if you're dealing with a plane problem where the row vector and the force vector don't have any z component, so in two-dimensional problems, the moment only has non-zero z component. Most of the stuff that we're going to do in this class is in 2 dimensions, so this is going to be an important fact for us. And we get so used to, when we're doing a lot of 2D problems, we get so used to thinking of the moment as just a single number. It's easy to forget the fact that it's really a vector. It's just only in the z direction. But that's an important thing to keep in mind, because when you go to 3 dimensions, it becomes a vector with 3 non-zero components. Okay, so here's the thing. This is the last thing I want to say. The pancake table. This is just something that students seem to like. As a way to organize your calculation of moments and organize your forces. It doesn't introduce any new information. It's just a simple table you can set up that keeps all your information in one place. You can use it the same way every time, and it helps you avoid errors, I think. And so here's the idea. I'll do a lot of examples that show how to fill this out. So the headings on the columns are P vector, A vector, row vector, force vector, and moment vector. And the mnemonic for this is pancake, artists, row, for, marzipan. Marzipan is like some kind of fancy frosting. I don't know if there's really anyone who puts marzipan on pancakes, but there it is. And notice the clever row and the Greek letter rho. And what these mean, this first one is the coordinates of the point where the force is applied. The second one is the coordinates of the about point. Once you've found both of those, rho is just equal to P minus A. F is the force vector. And then the moment, MA, is just equal to rho cross F. So you could set this up as a spreadsheet or whatever. You just fill out those values and then do the calculations. When you're done with a whole table, so one table corresponds to one free body diagram. And so fill out a line for each force that's being applied, each load that's being applied on the body. And then at the end you have a column that gives you all your forces for Newton's second law, and a column that gives you all your moments for the rotational equation. Okay, let's stop there, and we can talk about the test a little bit. And I'll start, I guess, on Monday, because we're going to spend the whole class tomorrow on the test. Monday, I'll go through some examples, rigid body problems using this table. Okay, so the test is going to be just based on those. So we're starting out kind of slow. It's going to be problems similar to the assignments up through yesterday. So the stuff that I'm going to ask you to do for today is not going to be on there. So I guess I remember what these are. That will not always be the case. But with vectors, it's all the problems. I think that's 1 through 11. And then particle free body diagrams. Uh, 1 and 4. Okay. So make sure you understand how to do those kind of problems. Also, go back through the related example problems, and if you can make sense out of those. I think, to me, the best explanation I can give for how you know whether you're ready or not is like, if you could go through these questions and explain to someone else how to do it, like why at each step you made the choice that you did, you're perfectly ready for the test. Okay. Okay, that's all.